We're going to look at quiz 3 for the general physics class. So this has 3 different questions. Let's start with the first one. Your friend is running towards you very fast while singing a perfect middle C. You are standing still though, and you are certain you hear a C sharp. How fast is your friend running towards you? Okay, so this is a Doppler shift problem. Your friend is running towards you singing at some frequency, but you hear a frequency that's actually higher than the one that they're emitting. And so it's a Doppler shift that's taking place, making you think you hear something higher. Well, you do hear something higher. If your friend was running away from you, you would hear a lower frequency or a lower pitch. I give you information. I say the frequency of a middle C is 261.63 hertz. Frequency of a C sharp is 277.18 hertz. I also give you other information. I tell you the velocity that you are at. Your velocity of the observer, you're the observer, is equal to 0. And we're solving for the velocity of the source. One other piece of information you need is the velocity of sound in air. So I'm going to say velocity of sound. That's about 340 meters per second. So let's write the equation for a Doppler shift. I give this to you. It says the frequency of the observer is equal to the frequency of the source times velocity, this is of sound, plus the velocity of the observer over velocity minus the velocity of the source. We're solving for velocity of the source. So let's divide both sides by frequency of the observer, multiply both sides by this denominator. Velocity minus velocity of the source is equal to frequency of the source over the observer times velocity plus velocity of the observer. Subtract v from both sides. And multiply both sides by -1. Now we've solved for the velocity of the source. Let's plug in all of the other values. Velocity of the source equals 340. Remember, this is the velocity of sound. Minus frequency of the source. The source is your friend who's singing. Frequency that you observe times the velocity again of sound plus velocity of the observer, which is 0. So I'm just going to multiply this out right now. 261.63 divided by 277.18 times 340. You get this is equal to 340 minus 320.9. These units are hertz, so the hertz units cancel out, and we're left with meters per second here, meters per second here. And so our final answer is 19.1 meters per second, which are the units that we would expect to get. So that's pretty fast, 19.1 meters per second. Maybe someone could do it for a short amount of time. And that's the answer for this problem. The key to this problem was understanding what each of these variables referred to. You're given the information, and then you just had to plug it in as the correct variable. Okay, the next problem says, the sun emits radiation with a total power of 3.8 times 10 to the 26 watts. So the total power of the sun is 3.8 times 10 to the 26 watts. The sun is located about 1.5 times 10 to the 11 meters from Earth. On a clear day, with the sun directly above you, how intense is the radiation that hits the Earth? Your units should be in watts per meter squared. Okay, so we're looking for intensity. We have an equation for intensity, and that's equal to power over area. This is specifically a surface area in this case. Let's try to visualize what this question is asking, though. The sun emits some amount of power, and this power comes off as a wavefront. As the power, or as a wavefront gets further away from the sun, the power has to be spread out over a larger surface area. That is, when it first leaves the sun, the power is spread out over some sphere. Let's say that's this big. But after a bit of time has passed, this wavefront gets larger. And you have a larger sphere over which the power is spread out. And so if I look close to the sun and look at some square meter, there's some intensity that's hitting that square meter. But if I look at the same square meter further out, the intensity drops because the entire power is spread over a larger surface area. That is what this equation is telling us. So we're given the power of the sun. We need to find the surface area over which this power is spread. Well, I tell you the Earth, let's say the Earth is right here, it's located a distance, we're going to call it r, equals 1.5 times 10 to the 11 meters. We know that the surface area of a sphere is 4 pi r squared. We know what r is. That's our radius of the sphere. That's also the distance from the sun to the Earth. We can plug it into this equation to solve for our area. We have our power. We have enough information to solve for the intensity. So the intensity is equal to this power, 3.8 times 10 to the 26 watts. And the surface area is 4 times pi times 1.5 times 10 to the 11 squared, meters squared. Because this is units of meters and we're squaring it. And so our total intensity will be in units of watts per meter squared. Now, just so I don't make any mistakes, I'm going to solve for the denominator first. 4 times pi times 1.5 times 10 to the 11 times 1.5 times 10 to the 11. And I get something like 3.8 times 10 to the 26 on top, and 2.83, I'm just going to add an extra figure in there, times 10 to the 23rd on the bottom. So just taking a look at this, how big should our final answer be? We have something times 10 to the 26 on top, something times 10 to the 23rd on the bottom. So our final answer should be something on the order of that 10 to the 26 minus 10 to the 23rd would be 10 to the 3. So on the order of a few thousand watts per meter squared. This is just to make sure that when you plug in your final answer, I know some people got an answer around 10 times 10 to the 49. And the way you got that answer was you did this times this divided by this, and then times this. When you put it into your calculator, you multiplied that whole thing by that instead of dividing by it. What you need to do when putting it into your calculator is do this times this, divided by this, divided by this, and then the correct answer will come out. So this is 3.8 times 10 to the 26 divided by, divided by 2.83 times 10 to the 23rd. And my calculator made a mistake. I need to put the parentheses in there. 3.8 times 10 to the 26 divided by parentheses 2.83 times 10 to the 23rd, close parenthesis. That's better. Okay. I got 1,342.8. That's watts per meter squared. Okay, so that's number 2. That means that here on Earth, if I look at 1 meter squared of space, we have that much power hitting it. And so another problem I was going to ask, but I didn't end up asking, was if we have a solar cell that's only, let's say, 30% efficient, how big does it need to be in order to generate some wattage? I was going to say maybe power a 60-watt light bulb. And we can figure that out, but we're not going to. But that is another question that I had in mind. So if you want to think of other ways to challenge yourself, you can try that. Let's go on to our last problem. Now, of course, that was that was considering that the sun's directly above us. We're not at some angle to the sun where we would get a smaller total flux coming at us. And it assumed it was a clear day, that none of this power was being absorbed by anything between the sun and the earth. This final question says, I have two speakers that are in phase, and they are next to each other playing a tone with constructive interference. So if I have two speakers, we could call it A and B. If they're in phase and they're next to each other, they're always going to be constructive interference. We know that because I gave you equations. This equation is for constructive interference, and this equation is for destructive interference, where n is equal to 0, 1, 2, and so on. Well, if it's constructive, if delta r is a path length difference, this is how much further one speaker has to travel to reach your ear. That's an ear. This is how much further one speaker has to travel to reach your ear than another speaker. In this case, both speakers are right next to each other. Delta r is equal to 0. That is, they travel the same distance. There's no difference between the distance. This is r1, the distance one speaker has to travel, or RA we could call it. This is RB. Delta R is equal to RB minus RA. In this case, RB and RA are the same, therefore delta R is 0. That means that no matter what value I put in for lambda, it'll be constructive interference, because the only way to make this correct is to have n equal to 0. And so our equation for this is 0 equals 0 times lambda. That means we're completely open as to what values we can choose for lambda so far. But I give you more information. I say when you move one speaker back by 0.5 meters, the sound becomes very soft due to destructive interference. And I ask, what is the frequency being played? So when I move one speaker back by 0.5 meters, we'll say this distance is 0.5 meters. And I have another speaker that's right here. It's destructive interference. I'm hearing, that's my ear again. I'm hearing destructive interference. I kind of tried to draw this correctly, showing that they're both in phase, but we have a trough here interfering with a crest. We have a crest here interfering with the trough, and so on and so on. And that will create destructive interference at my ear. I could visually try to solve for this and I'd say, oh, it looks like half of a wavelength corresponds to half of a meter. Therefore, a whole wavelength will correspond to 1 meter. But you may have not known how to draw this, and there are also different ways to draw this. Instead of solving for this visually, let's solve for it using this equation. So in this equation, delta R, the path length difference, is 0.5. That is, one speaker travels some distance, other speaker travels some distance. We'll call this distance R sub B. The distance that R sub A travels is equal to R sub B plus 0.5. Therefore, path length difference is equal to 0.5 meters. I just made it an absolute value. We know we have destructive interference when our path length difference is 0.5 meters. And so our equation, when we plug it into our destructive one, is 0.5 meters equals n plus 1/2 times lambda, our wavelength. It is kind of a tricky question, but not really. The tricky part now is, what value of n do I need? Because once I plug in n, I can solve for the wavelength. Once I know the wavelength, I can solve for the frequency. The answer is you can plug in any value of n. Up here we used n equals 0, but that corresponded to a very specific situation. Right here, we could have any value of n, and that will give us a correct answer. Let's look at two values of n. Let's plug in n equals 0, solve for it, and let's plug in n equals 1 and solve for it. If I plug in n equals 0, I get 0.5 equals 0.5 times a wavelength. Say wavelength is equal to 1 meter. That's the situation I drew here. I drew half of a meter corresponding half of a wavelength, therefore an entire wavelength corresponded to a meter. That was the most intuitive answer to me. If the wavelength is 1 meter, we can solve for the frequency because we have an equation that velocity is equal to wavelength times frequency. The velocity is the velocity of sound in air. These are sound waves traveling through air. So 340 equals 1 times frequency. The frequency was 340 hertz. So this corresponds to our situation with n equals 0. Let's see what happens if we plug in instead n equals 1. I'm going to erase this situation. We're going to plug n equals 1 into here. So our path length difference is still 0.5 meters. We didn't change that. We're going to say this is 1.5, because I'm plugging 1 in for n, times lambda. Lambda is equal to 1/3 meters in this case. Let's see if we can draw this. So I'm going to use the same situation, or same axes, but now my wavelength is 1/3 of a meter. So let me draw 1 meter marks. Right here's 1 meter. I guess 2 meters will be right here. If it's 1/3 of a meter, that means I have it pass through here, then here. It's going to look like this. There's 1 wavelength, 2 wavelengths, 3 wavelengths, and so on. If I have the same case right here, let's try to make our meter the same length. Maybe this is a meter. Try to get our tick marks at every 1/3 of a meter. I think that's a little too far, right there. If I draw it, it starts by, I wish this was over just a little more, but we can see what I'm looking at. There's 1 wave, there's 2 waves, there's 3 waves. And what we get is a situation where, again, this crest and this trough are going to match up, and this crest and this trough are going to match up, such that we still get destructive interference. I didn't draw this quite at the beginning. Let's see if I can make it a little bit better. I'm going to make the wave start where speaker B is located. It's about that far. We have 1 there, 1 there. Something like that, where the wave and the crest, the trough and the crest match, trough and the crest match, trough and the crest match. And so here's another situation where I can move it 0.5 meters back and still get destructive interference. The way we still got destructive interference is because earlier I moved it half a wavelength back. Now I'm moving it 1.5 wavelengths back. Every time you move it some total of something and a half wavelengths, you're going to get destructive interference. While if you move it a whole number of wavelengths, you're going to get constructive interference. So this is 1.5 wavelengths. That's what the path length difference is right there. That's exactly what that equation gave to us. Again, we could have plugged in any value for n. You could have plugged in 100 for n if you really wanted to, and you'd still get a correct answer. It just referred to waves that are very small, but you still would have moved it a total of however many, 100.5 wavelengths back from where its original position was. We just make the wavelengths very small. Okay, that's the end of that quiz.